Over the last few weeks, we've been looking at questions calculating speed from distance and time. The main things that we've seen are the formula, speed equals distance over time, which we can rearrange to distance equals speed times time, or time equals distance divided by speed. We've also looked at the importance of making sure that our units are consistent. So if we're measuring distances in meters and time in seconds, our speed will be in meters per second. But if we're measuring our distances in kilometers and our times in hours, our speed will be in kilometers per hour. But all the calculations we have done have been looking at an average speed. In reality, that's not the way things are. When a car goes on a journey, it changes direction, it speeds up, it slows down. But if we look at the records on the car, it'll tell us how far it's gone and we can measure the length of time. It'll give us an average speed. The speed and direction changes, and the pure numbers of how far the car has gone and the time it's taken to do that don't really tell us anything about the actual journey. Let's consider a car on a more straightforward journey. Here we can see that every second the car is moving forward about 2 meters and it's moving at a steady speed. In this case, it travelled 14 meters in a time of 7 seconds, so that's going to be 2 meters per second, 14 divided by 7. But it can often be very useful to display this information in a graph. Let's run through this again. Here I've got a graph, and we're going to plot distance travelled on the y-axis against time on the x-axis. We'll call this a distance time graph. And the graph is going to show how far the car has travelled at any particular time. So as it moves forward, the line moves up the graph. The advantage of this means it allows us to tell us how far the car has gone at any particular time. We can also work out the average speed of the car from this graph, and that's by using something called the gradient. The gradient of this line equals speed. In physics, we have to measure the gradient of a line an awful lot. In speed and motion graphs, in electricity, VI graphs, for density, mass and volume graphs, we use it an awful lot. So this is a skill that you'll be using repeatedly. What do we mean by the gradient? The gradient is the slope of the line, how steep it is. And the simplest way of working it out is by saying that the gradient is equal to the rise over the run. Rise divided by the run. The rise is how much the graph has gone up, in this case 14. And the run is how far the line has gone across, which in this case is 7 seconds. So the gradient is the rise over the run. So it's 14 over 7, and 14 over 7 is 2. So the speed is 2 meters per second. That's a very straightforward graph. And it doesn't seem to give us much advantage over what we've been doing already. We know the distance travelled and the time taken. There is an advantage. We could say, well, at 4 seconds, how far has it gone? We can look at the graph and go to 4 seconds, go up and across, and we see it's at 8 meters. Or if I said, how long does it take to travel 7 meters? I could go to 7, halfway between 6 and 8, go across, go down, that'll be 3.5 seconds. Where this really is useful is whenever we have a car or an object that's travelling at a non-steady speed. Let's look at the graph for this journey. We saw that for the first 4 seconds, the car travelled quite slowly, and then it accelerated, it sped up for the remaining 3 seconds. Now, if we looked at just the final distances and times, we would see that the car had travelled a distance of 14 meters. That would be our rise. And our run, the time taken, would be 7 seconds. And if we found a gradient for that, 14 over 7 equals 2 meters per second. The average speed is 2 meters per second because it's travelled 14 meters in 7 seconds. But at no point did the car actually travel at 2 meters per second. It had different actual speeds. And the graph allows us to work out what those speeds are. And we can do that by finding the gradient of each individual section. So let's look at the first section of the graph from 0 to 4 seconds. There's a rise and a run for that section. The rise is 5 meters and the run was 4 seconds. So gradient equals rise over run. So it's 5 over 4 equals 1.25. So the speed for that first section is 1.25 meters per second. We can apply the same technique to the following 3 seconds. We've got a rise and we've got a run. The rise is 9 meters this time, from 5 up to 14. The run is from 4 to 7, so that's 3 seconds. Gradient equals 9 over 3, rise over run, equals 3 meters per second. So for the first part of the journey, the car travelled at 1.25 meters per second, the second half of the journey for 3 meters per second. So the graph allows us to get a lot more detail about the actual specifics of the journey. Let's try this again. Here our car goes forward, but now it's stopped for a while. And it starts moving again. And we get this very distinctive shape in the graph, which I'm going to split up into 3 sections, A, B, and C. A, rise of 6, run of 2. So it's speed equals 6 over 2 equals 3 meters per second. This middle section, B, well, there was no rise. The run was 2 seconds, from 2 to 4, but there's no rise. So the speed is 0 over 2, 0 meters per second. So if we see a distance time graph with a horizontal section in it, as we do here, we know that that object was stationary at that point. For section C, well, our rise is from 6 up to 14, which is 8 meters. Our run is from 4 seconds up to 7 seconds, which is 3 seconds. So our speed is 8 over 3, which is 2.7 or 2.67 meters per second. Notice the average speed of this journey is exactly the same as before. It took 7 seconds to travel 14 meters. But clearly there's an awful lot more detail that can be discerned from this graph. One important thing to note is that you cannot find an average speed by adding up the individual speeds. Here we've got a speed of 3 plus 0 plus 2.7, so that's 5.7. And 5.7 divided by 3 is about 1.9. Now that's not the average speed. The average speed was 2. It was 14 divided by 7. So you can never simply add up the individual speeds of a journey and divide them by the total number of speeds to find the average. That does not work. The only way you can find the average is by doing the total distance divided by the total time. Let's look at one more example of a graph like this. Our car moves forward quite quickly, it stops, and it reverses and stops again. We saw that the car was going quite quickly, and we can see that in the graph by the line being steeper. Again, section A in this case travelled from 0 to 12 meters, so that's a rise of 12 meters, and a run of 3 seconds. So 12 divided by 3 equals 4 meters per second. Again, section B, there was no rise for a run of 1 second, so the speed is 0. It's stationary again. For C this time, well, the rise is negative. It goes from 12 down to 0. So we've got a negative rise. Our run is still 2 seconds. So our speed is negative 12 divided by 2 equals negative 6 meters per second. What does that negative mean? It doesn't mean that it's travelling less than nothing. It just means it's travelling backwards. And that gets us into the concept of something called displacement, which we're not going to concern ourselves with now. But we can see that if a graph is going upwards in this case, as in section A, the car is moving forwards. As it comes backwards, the graph's going to go downwards, as in section C. Section B, graph's horizontal, car's not moving. There's also a little bit at the end between 6 and 7 seconds. The car was stationary there as well. It's also horizontal. By looking at the graph, we can see that line C is a bit steeper than line A, so it's moving faster, and the numbers bear that out. We can see it's moving at 6 meters per second instead of 4. In your notes, we'll cover this a bit, and there are some questions for you to do.